All right, we're going to start our series unit. I gave a little bit of an overview of this in class, so this should not be entirely new. And again, we saw a lot of this last year in pre-cal as well. Different BC Calculus courses will do this in different orders. The Forrester book actually starts with the Power series, Taylor-Maclaurin series, those types of things representing polynomial functions, or actually non-polynomial functions like the sine function and e to the x, in a polynomial form as infinite series. We're going to start in the other direction. We're actually going to talk about convergence and convergence tests first, which are a big part of the AP exam. Once we've got a good handle on that, we'll go look at some specific series and be able to handle the convergence at the same time. So we're going to be starting out here with geometric series. Just as kind of a reminder of how geometric series work, if you think back to Algebra 2 in pre-cal, a sequence is just a list of numbers with some kind of a pattern. Okay, very, very simple idea, very straightforward. A series is a sum of a sequence, okay? And that's what we're going to be looking at in most of these cases, all right? So anyway, you can see here, got a couple examples of some different geometric series. A geometric series has a multiplying pattern. If you remember, an arithmetic sequence has an adding or subtracting pattern. So notice here, we're multiplying by 3, continuing to multiply by 3, okay? A geometric series, or just series in general, can also be used, written using sigma notation. You'll see different types of setups, but typically you'll see whatever your variable is, maybe an n and a k, something like that, either starting at 0 or 1, okay? So you can start with the 0th term, or you can start with the first term, and that's something that can vary a little bit, just kind of based on how your variables are set up in the first place. So for example, if I was trying to represent this, maybe I could do something like n equals, actually I could do something like n equals 0 to infinity. You're actually starting out with 4, and then you're multiplying by 3 each additional time. So you have 4 here, and then you can say that it gets multiplied by 3, and of course it's going to be continuously multiplied by 3, so it's going to be 3 to a power. If I start n at 0, then I can say it's 4 times 3 to the n. When n is equal to 0, that would actually be my first term. 3 to 0 would be 1, and I would start out with the first term of 4. And then when n becomes 1, I would have a term of 4 times 3, which is 12. And then when n is 2, I would have 4 times 9, which is 36, and so on. Okay? If I wanted to start this out with n equaling 1, I just need to change my exponent. You would change your exponent here to be an n minus 1, okay? And then when n is 1, this exponent would be 0. 3 to 0 times 4 still gives you 4. When n is equal to 2, that would be 4 times 3 to the first. You'd still get 12. So just watch that. There's not a right or wrong. Actually, I think a lot of what we'll work with down the road, you'll be starting at 0. I think we'll see a decent number right now that start with 1. But again, it really shouldn't matter. If you don't like sigma notation, if you don't recognize what's happening, just write out a couple of terms and everything should become pretty clear. Okay, coming back here to this geometric series. So you're consistently multiplying by 3 here. We say that the R value would be 3, okay? This is a series that we say is divergent, okay? A divergent series just basically has no overall sum, all right? If you keep adding this up, the numbers keep getting bigger. Basically, it adds up to infinity, okay? It is possible to have terms that are decreasing, and they could be all positive terms decreasing, or it could also be an alternating series, switching back and forth between positive and negative. And if the terms are getting closer and closer to 0 as you go, that means it's a decreasing series, and that means that it has the possibility that this series may approach some sum. Now we need to be really careful with this, because I think there's a tendency for people just to think, oh, I have a series that decreases to 0. As long as the terms decrease to 0, it's always going to have some kind of a sum, and that's not necessarily the case, and that's what makes this such a challenging topic, because You know, whatever your instinct is for one kind of problem doesn't necessarily work for another kind of series. So we're going to see that. But anyway, notice in this case we have decreasing terms. Our R value there would be equal to 1/2, okay? And so in this particular example, this will have a sum. If you remember, the sum of infinitely many terms of a geometric series, and this is really important, is the first term divided by 1 minus the common ratio. Okay, so you can see in this particular example here, the first term is 8, the common ratio is 1/2, 8 divided by 1/2 is going to be 16. Okay, so we would say that this is a convergent series, or that the series converges. Basically that would mean that if you keep adding up terms, they're going to get really close to 16. Okay, they can get infinitely close to 16, and that's what makes it a convergent series. All right, so that's kind of the basic idea. Now, where do we go from there? Well, basically, I'm going to give you different series, and I'm going to ask you if it's convergent or divergent. And one of the easiest series to recognize on the AP exam is geometric series. They're not super common. It's not really what the course is about, but it is a series they will probably toss in somewhere at some point. So it's one of the first things that I always check for. Okay, and the key is you just have to remember, geometric series only converge if R is between 1 and -1, okay? Or some books will say if the absolute value of R is less than 1, okay? And that concept is going to be really important for some other types of tests that we're going to work with down the road, even for some series that aren't necessarily geometric, okay? Now, what are typical problems going to look like? Well, if you took a look at a BC exam, you would see a whole lot of sigmas popping up all over the place. And that can be a little bit disturbing to people at the start. So you might see something like n equals 0 to infinity, and you've got a series like 4 to the n over 5 to the n, okay? You could write out a few terms. If n is equal to 0, your first term is going to be 1. If n is equal to 1, your next term is going to be 4/5. If n is equal to 2, your next term is going to be 16/25. And you could look to see, am I consistently multiplying by the same value? If so, what's my R value? And so on. And you can see here, the numerators are always being multiplied by 4. The denominators are always being multiplied by 5. Okay, the R value here is 4/5. That is between -1 and 1. This is a convergent geometric series, all right? Now, that's one way to look at it, okay? The other way to look at it is just to get kind of used to working with this setup, okay? And you could say, for example, I want to see what I'm consistently multiplying by. If you take a number to a power, that power applies to both the numerator and the denominator. So a second approach would be to write that as 4/5 being taken to the n power. And then you can see, oh, each additional time I'm multiplying by 4/5 again, you can just see the R value sitting right there. And you can tell that in this particular case, A, it's going to be geometric, B, it's going to have an R value that's between -1 and 1, and so it's going to converge. So again, some of these you'll be able to look at and just spot it. In a lot of these, you're going to have to do some maneuvering, okay? So let's look at another example that might involve some of that maneuvering. Let's say I've got something like this. I'm going to start it at 1 this time for a reason you'll see in just a second. It's going to go to infinity. And I've got 5 to the n over 2 to the n minus 1. Okay? A lot of times your exponents aren't going to match. And again, you could list out terms and you can see what's going to happen. Or you can try to manipulate the statement and see if you can get it to look something like this. By the way, the notation that they'll normally use, they'll normally say that the series, they'll say something like a times r to the n minus 1 from n equals 1 to infinity converges if r is between 1 and -1, something like that. In other words, you've got a first term. This is implying that if n is 1, that'll start out at the 0 power. And so that's kind of your basic format. Okay, and by the way, if you think back to Algebra 2 at pre-cal, A sub n equals a sub 1 times r to the n minus 1. That's the nth term expression that you're seeing there, and you know, it's just generating the nth term for whatever value of n you substitute into the equation. So, you know, that's something, if you look up a geometric series in a textbook, that's going to be kind of the formal definition they're going to give you with the sigma notation. Okay? This one here, if you notice, you could factor a 5 out in front, and you could get it to kind of match this format that's got a leading coefficient. Bring 1 5 out in front, and that's going to drop your power by 1. Okay? So now you have 5 halves, that whole numerator denominator taking the n minus 1 power. So you could write that as 5 halves raised to the n minus 1 power. And hopefully you can see now, when n's equal to 1, that's going to be a 0 power. This goes away, just becomes 1. 5 times 1 is 5. That's your first term. And then after that, when n is equal to 2, you're going to have 25 halves. And when n is equal to 3, you're going to have 125 over 4, and so on. And anyway, hopefully you can see here, you're really just multiplying by 5 halves each time. And of course, 5 halves is 2.5. This is an increasing series, okay? So this is going to diverge. There is not going to be a sum there, okay? By the way, this one would be convergent if you were finding the sum. This one would actually start out at 1. And then it would go to 4/5, and then it would go to 16 25ths, and so on. If you were asked to find the sum, you'd be taking the first term divided by 1 minus the common ratio, and I think that's going to work out to be 5, right? Because it's going to be 1 divided by 1/5. So again, most of the series we're going to work with, you're just going to be asked to find if they converge or diverge. But you're occasionally going to be asked to you're occasionally going to be asked to actually find the sum, and for geometric series, those are usually going to be the ones where you actually can find the sum. Okay, so that's something to keep in mind. Let's look at a third example here. Okay, a third example. Sometimes they'll give you things that don't look anything like any of the other examples I gave you. Let's do something like n equals 1 to infinity of 3 to the 2n times 5 to the 1 minus n. Okay? Again, you're normally multiplying by a fractional value, so you'd like to see a fraction in your statement. On the surface, you just say, well, look, I'm multiplying by 3 and 5. You know, that could be like multiples of 15 or something like that. But be careful, because remember that you can rewrite these values. You could switch a sign on one of those exponents, and you could rewrite it in a fractional form, and then you can kind of manipulate it around, and you can see what you're consistently multiplying by, which might be a good idea, okay? Because right now, as n grows, like when n is 2, you're going to have a negative exponent there. So let's just tweak this, okay? So I'm going to move the 5 to the denominator, but I'm going to switch the signs on that exponent. So instead of a 1 minus n, the n is going to become positive, and the 1 is going to become negative. I've switched the sign on the exponent. And now we can kind of rewrite this. You really want to write something to like the n power, the n minus 1 power. You really want them both taken to consistent powers. One of the things I noticed, this is 3 squared to the n power, if you think about taking a power to a power, multiplying your exponents. Okay, this is still 5 to the n minus 1 power. I'd like these exponents to match up. First of all, 3 squared is 9. Okay, and I would replace that 3 squared now with a 9. And you can factor out one of those 9s, bring it out in front, and that's going to drop your exponent down by 1. Okay, now notice something. These are both being taken to the n minus 1 power, which means I can rewrite this as the fraction 9/5 being taken to the n minus 1 power. And now hopefully you can see I'm consistently multiplying by 9/5. Okay, 9/5 is greater than 1. That is a divergent series. Okay, the terms are increasing, and at that point we're done. All right, so that's kind of an overview of the basics to recognizing geometric series, both deciding if they converge or diverge, but also finding the sum. So that'll give us a little bit of insight, and then I'll build on this in coming lessons.